In this video, we're going to look at two questions on the topic of photoelectric effect. So first of all, it says a lithium surface with work function energy W is equal to 3.7 times 10 to the minus 19 joules is irradiated with photons of frequency f is equal to 6.3 times 10 to the 14 hertz. And then the loss of photoelectrons from the surface causes the metal to acquire a positive potential V. What will this potential be when the metal prevents the loss of further electrons? So first of all, the question wants to calculate the potential when the metal prevents the loss of further electrons, and that is supposed to be the stopping potential. So yeah, so that is essentially the maximum potential that can be generated. So let's write down the equation first. What we know is that the maximum energy of the photoelectrons is equal to the energy of the photons minus the work function. So what we can do is that we can convert energy into electron volts. So that will be essentially the charge of the electron times the potential. That is essentially the stopping potential. And then over here we have HF minus W. So from this, we know the charge of electron, we know Planck's constant, we know frequency, and the work function is given, so we can directly calculate the potential. So over here, that will be Planck's constant is 6.63 times 10 to the minus 34 times the frequency, which is given as 6.3 times 10 to the 14 minus the work function, that is minus 19 over the charge of electrons, and that will be 1.602 times 10 to the minus 19. And we put this into a calculator. Over here we have 6.63 and then times 6.3, 14 minus 19. So that will be equal to this, and then this then divided by 602 minus 19. Okay, now that will be equal to 0. Let's go to 3 significant figures. That will be 298 volts. And that will be the answer to the question. Now let's see the second question over here. In the photoelectric effect, an electrode is placed 0.1 meter from a clean sodium surface, which has a work function of 2.28 electron volts. Okay, so it looks something like this. That will be, this is sodium surface, and then over here it says an electrode. It doesn't say what kind of metal, but the basic idea is this. I suppose it's connected to like a circuit. I won't draw the full system first. So this is the idea. It says light wavelength is shown on the surface and electrons are emitted. So the idea is that light is shown on the surface. Let's say the left side is the sodium surface, and then essentially there will be photoelectrons that are emitted from the surface, which goes over here. And then short time. Okay, so the first component of the question was to calculate the shortest time it takes the most energetic photoelectrons to reach the electrode after illumination started. So let's see. It's the same equation as the last question. Over here, E max is equal to HF minus work function, and then the work function is given over here. So we can convert E max into a half mv squared, and E, the mass of electron, and then the same thing. And what I want to calculate is the velocity of the electrons, and then we can just divide the distance between the plates, which is given as 0.1 meters, with velocity, and we can get the time. That is essentially the shortest time to reach the electrode. Okay. So over here, CV squared is equal to 2 times, this is Planck's constant, times the frequency, and frequency is given as, okay, so wavelength is given to the frequency. Frequency is equal to the speed of light divided by the wavelength. And then we can just write this, okay? And then minus the work function, which is 2.28. And then I'm going to convert it into joules. So that will be, let's see, times the elemental charge. Okay. And then down there, it's divided by the mass of an electron, which is 9.11 times 10 to the minus 31. And then we can put this entire thing into a calculator and get a value for the velocity of the electron. 2 times Planck's constant, and then times the frequency. Speed of light over wavelength minus 9, and then over here we have minus the work function converted into joules. Okay, and down there we have the mass of an electron, so that will be minus 31. Okay, and this is what we get, and we also cannot forget to take the square root, and that will be equal to, let's see, I'm going to leave it for 6 significant figures, so that will be 311 meters per second. And then the time will be equal to the distance divided by the velocity. Distance, I remember that is 0.1 meters, yes. And then divided by the velocity. Okay, and that will be equal to 0.1 over this. That will be 1.858 times 10 to the, that is minus 7, yeah, minus 7 seconds. And that will be the answer to the first part of the question. Now let's see the second part. Over here it says a stopping potential of 0.5 volts is applied between a plane electrode parallel to the photoemissive surface to produce a uniform electric field. What is now the shortest time it takes the most interjected photoelectrons to reach the electrode after illumination is started? Okay, so it says a stopping potential is applied. So this essentially means that this is opposing to the potential that is generated by the photoelectric effect. So my idea is that we can take a value from the previous question. So over here, the idea is this. Right now, the new maximum energy will be equal to the energy of the photons minus the work function, and then minus the new potential. I'm going to say Vs for stopping potential. So yeah, so then my idea is that we can do exactly the same thing as the last question and then get the answer for the minimum time. Okay, so over here that will be a half MEV squared is equal to 3 minus 34 times that is speed of light over the wavelength, and then minus the work function. I'm going to do this because both of them will be multiplied by the elemental charge. Okay, so the time potential applied is 0.5, 0.5 plus a 0.5, and then both of them timed by the elemental charge, or the charge of an electron. And then, let's see, I'm going to say v squared will be equal to, so over here we have Planck's constant, and then times h divided by the wavelength, and then minus plus 0.5 times the elemental charge. And this is what we get. And then what we do is time this by 2 and divide it by the mass of an electron, which is minus 31. Okay, and this is what we get over here. So that will be 113. I'm going to say times 10 to the 9 meters per second. No, this is not meters per second. And then v will be equal to the square root of this, and that will be equal to 337,531. I'm going to say 6 significant figures, meters per second. Okay, now we can calculate the time. So the time taken will be equal to the distance divided by the velocity, which is 0.1 divided by what we got, and that will be equal to wait no, so that will be equal to 0.1 over 337,532, and that will be equal to, I'm going to say 2.96 times 10 to the power of minus 7 seconds, and that will be answer to the question.